Okay, let's go ahead and so we'll start with a limiting reactant one, like Sherry has asked for. So, as always, I know you guys love your word problems, so we'll start with one. This one is definitely longer than something that you would expect on your exam, but it has a lot of things we can kind of practice in the meantime. So it'll be nice and kind of efficient for us with our review here. So we'll be taking 3.24 grams of sodium sulfate, mixing that with a certain volume of a certain concentration of calcium chloride, and we're asked what mass of the solid product that's produced, assuming that we have 100% yield for this reaction. So let's go ahead and see what we can digest here with light blue, of course. So we have information about one of our reactants, and we have information about the second reactant, and then the question that we're asking for is the mass of the solid product. So that's going to tell us there's probably a precipitation happening, right? That's where we would get a solid product from a sort of reaction like this. So those are kind of the important bits there, those three kind of points of information that we're going to want to work with here. So we're going to want to start off by taking a look at what this reaction would do. And just to maybe clarify, if this was your exam, like this is kind of 3 questions in one that we're doing right now. So you would not have something this long again. So one, I could just ask you what's the balanced equation between them, what are the states of matter going on there, and then I could ask you the mass of the product that we're looking for. So totally loud plane going outside. That's fun. Let's go ahead and finish this reaction here. So, wow, that's really quite loud, huh? We'll wait for that to go blow over. Okay, there we go. So this being a double displacement reaction, of course, our products would be the kind of swapped pairs of those. If we are to balance it, we would see that we would get a 2 there. If we're to put our states of matter in, remember, you guys do not need to know about the states of matter for the reactants, because that information will be from the problem. So we're given grams of sodium sulfate, so that tells us it's a mass, and masses are for pure substances. So sodium sulfate being ionic should be a solid at room temperature. And then the other one is aqueous, because we're given that it's a solution. So we're as chemists, of course, we are should be able to predict the solubility of our products here. Sodium chloride we should get is soluble, and then we're going to see that the calcium sulfate there should be insoluble. So since we're asked for what the mass of the solid product is, that's going to be this guy here. Creature, shush. You don't have to be naughty. Okay. So we have these 2 bits, and then we're looking for calcium sulfate. So now we can finally do our stoichiometry stuff. So because we have information about 2 reactants, this is going to be a limiting reactant problem. So that would tell us, okay, we have to take our first one and convert this into grams of calcium sulfate, which we can do. Gonna quickly just look up the molar masses because nobody wants to waste time on that. Sodium sulfate is 142.04. Okay. Oh no, the plane is back. Already. Looking at our reaction coefficients here, we have the same thing. One for each one. And then calcium sulfate we can look up as well. The molar mass of 136.14. So, doing that, all this lovely math, our favorite thing, 3.24 times 136.14. We get 3.105 grams. Okay, cool. So that's one of them down. Remember, limiting reactant, we have to do it twice, or as many as reactants as we have, and we want to compare our answers and choose the smallest one. So the next one we have is a solution. So with solutions, remember, we don't find the moles using molar mass, we use the molarity, right? That's our conversion factor between volume and moles there. So let's start out with that. I'm going to just go ahead and convert it to liters, if that's okay with everyone, because that should be second nature by now. Our molarity was 0.25. This is, of course, what are we? Calcium chloride. This is 1 mole of calcium sulfate. And since, again, we're asked for mass of calcium sulfate, that's when we're going to use our molar mass. And let's go ahead and do this. 0.02821 times 0.25 times 136.14. We get 0.9601. And so from this, now at the end of our problem, we can go ahead and take a look at our answers, and we're going to want to choose the smaller one. So that will be this one. So this would be our theoretical yield. Though because the question has said we have 100% yield, that is the same thing as our actual yield, but we won't worry about that. And so this tells us that the limiting reactant was calcium chloride. Okay, so depending on what question you're asked, you may be asked, instead of what's the mass of whatever, you might be just asked what's the limiting reactant. And for that one, you would choose the reactant that's going to give you the theoretical yield. What else could I do with this one? If I were to just take this question and instead of asking what is the mass of the solid product, I could just ask what's the limiting reactant, and you would just choose a product to go for. You wouldn't, as long as you choose the same one you can compare. So you could choose sodium chloride or you could choose calcium sulfate, doesn't matter. And in fact, you could just end at moles if you wanted. You wouldn't need to do the molar mass step, so you could save a bit of time there. And so yeah, so that would work. Let's see, anything else on this that I want to bring up? Make sure, again, you're very good with your naming. It's been a while since I've written this final, so it would. I guess one thing I could do is give you the names instead of formulas. Give them as names instead. But again, that would be another step. So that would probably just be like, what's the what are the products when you mix sodium sulfate and calcium chloride? And you would just answer based on that. So cool. Yeah, that's I guess kind of all I can do with this question. So, any questions on this stuff? Wow, on our very last day, we still have the spam. Wow. And look, there's really like only one word that's not a complete disaster. Let's write to them. There we go. Okay, well, then in that case, what else do we have? If Lamonda's here, I hope you were able to look at post-exam review 4, because we definitely did that question there. So in the meantime, we can go ahead. I think Sherry also asked a limiting reactant question, so there should be at least one more in that post-exam review for limiting reactant, so that would be a good place. Okay, so electron configuration and intermolecular forces. Ooh, okay, we can do this. All right. Awesome. Okay, cool. Alrighty, so here's a question for us. What is the electron configuration of the selenide ion? For practice, let's do this both ways. Let's do kind of the like expanded and the noble gas way. Oops. All right, selenide ion. What the heck is that? Well, remember that ide endings typically are for one element when it's in its negative state. So that means that this came from selenium. And so, since it is the selenide ion, it would be the preferred charge of selenium. If we find selenium on the periodic table, it is over here, number 34. Looks very boring, but I guess that's kind of silly for us to have it. No. Show us the table. Okay. Selenium, as we can see, perhaps, is in group 6 or 16. So that tells us it has 6 valence electrons normally. So it's going to be looking to gain 2, right? So selenium would normally take a -2 charge. So with that in mind, now we can go ahead and do our configuration, which I guess I have to go back to the periodic table for. So let's find where it's going to end. So we're going to see that selenium is in the P block. Remember, this kind of right side thing is the P block. And I'm kind of circling here. That's the P block. So selenium is in the 4th column of the P block, which tells us it's going to be something P4. If we look at our rows, it's in the 4th row of the periodic table. So that tells us its last electrons are going to be 4p. I'm sorry, 4p4. Let me get the right element here. Okay, so with that in mind, we know that it's going to end with 4p4. So we're going to have to basically just fill in everything that comes before it. You can use either the periodic table or that mnemonic device. Remember the like putting it out like this, etc. That triangle thing. You can do that either way. What we end up getting, of course, is going backwards. Remember that it's 3d10 that comes before it, even though it's in the 4th row, because d is always one less. 3s2, 2p6, 2s2, 1s2. Is that all of them? Looks like it. Okay, cool. Yes, and then of course the noble gas one, Brittany's already done for us. Yeah, that's how it would look. 4s2, 3d10, and then 4p4. Let me just double check the noble gas there. Yep, that's it. Okay. So, remember that all this stuff is argon. So we just need to put everything that's after argon for the noble gas configuration of it. Oh, and since we're so silly, this is technically for selenium, isn't it? But that's not what was asked. We were asked for the selenide ion, which tells us it has 2 more electrons, right? So if it was here, and we're going to give it 2 more electrons, that's going to make it essentially resemble krypton, right? Giving it 2 more electrons, we're going to just have to add those in. So if it normally is 4p4, we want to give it 2 more electrons. That's going to make it 4p6. And same thing for this one, right? Because 6, of course, being 4 plus 2. Tough math there. And so that's where these are going to be coming from. So make sure to read the question, I suppose, so that we actually are answering what's asked of us rather than something similar. Okay, let's see. What else can we do with electron configurations? Honestly, there's not much. I mean, if there's more specific stuff that we'd like to go over with electron configurations, we can. But I mean, it's kind of, I can ask you the configuration. Oh, I know what I could ask you. Okay, how about this? How about this? What element shall we choose? How about iodine? That's something that deals with... Now, this just looks like a grammatically terrible sentence. But instead of I being the pronoun for me, I mean iodine. So, not how many core electrons does I have. I have quite a few core electrons, but let's go ahead and find iodine here. So remember, technically we don't need to do the configuration to figure this out, but we could if we really wanted. So iodine is here. If we go ahead and look at where iodine is, it is in group 7 or 17, depending on your periodic table, which tells us that it has 7 valence electrons, right? Its atomic number is 54. We just saw that, perhaps. Remember that electrons can only be core or valence. That's it. So if we know we have 7 valence electrons, we can... Actually, it's 53, isn't it? I don't know how to copy numbers. It is 53. Okay. Is that necessary? Yes, I thought so. Okay, so that tells us that the core electrons overall should be 46. Hooray! If we wanted to really do that, we could throw out its electron configuration. 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. So there's this electron configuration. The core stuff should be all of these. Don't forget those 4d electrons are part of the core. If you had infinite time for some reason, you could technically add up all these numbers and you should get 46 also, but that takes more time. I would avoid doing the electron configuration if you don't need to. This way, I think, would be the way to go for this sort of problem. However, if you were asked something like, this, technically, again, you don't need to do the entire configuration for this. I'll show you what I mean in a sec, but if you have the configuration already, for some reason, this would be something that it would be more useful for if you're looking at specific electrons. So, for example, you would say, okay, we've got 6 here, 12, 18, 23 electrons there in p orbitals. So that was 6 plus 6 plus 6 plus 5, which was 23. However, lucky us, we could get this information from the periodic table as well. Let's go ahead and have a look. P block here, not helium. Of course, helium doesn't count in the P block because it's 2s. If we look here, we have 6 elements in the P block, another 6, another 6, and then only 5 up till iodine. If we're only looking at p electrons, it has to have these 6, it has to have these 6, it has to have these 6, and then we're going to see 5 more. So we can just add up, 6 plus 6 plus 6 plus 5, and that should give us our 23 as well. So you could use the periodic table to do that as well. Maybe a little faster that way. I'm not sure what else I can ask because we've pretty much exhausted our resources on electron configurations. But is there anything else, if Sherry's here, that maybe I didn't go over with electron configurations? Otherwise, we'll move to intermolecular forces. All right, cool. So, and then looks like Crystal wants to do some density stuff here. We could do that. Alrighty, let's talk about intermolecular forces. Crash course in it. All right, we've got kind of 4 forces that we're dealing with here. Okay, cool. Good. Yes. Boom, boom, boom. Okay, so we're going to do our quick crash course. Here we have 4 types, right? And they are, in this case, arranged in strength. Ion dipole being the strongest, London being the weakest. If we want to think about what can undergo London dispersion forces, that's everything. Things that are polar, things that are nonpolar. Dipole-dipole interactions are for polar things only. Hydrogen bonds are polar things with H on oxygen, H on nitrogen, or H on fluorine. And then ion dipole would be something that is like a salt dissolved in water. So, couple example here. These are going to be all your hydrocarbons. whatever they happen to be. Your dipole stuff would be when you're having polar molecules. So that would be, for example, something polar like this. I don't know, what else do we have? Carbon monoxide is polar also. And let's see, stuff with hydrogen bonds, that would be like ammonia or water or like methanol. Those things would be able to hydrogen bond. Of course, plain old single atoms can also do this. All your nonpolar stuff, again, your hydrocarbons are big things of the London forces. And then something like ion dipole would be a dissolved salt. So something like sodium ions dissolved in water. So one thing also to think about, oops. What's the word I'm thinking of? Not impermanent. I don't want to say transient either, but just induced dipole. Yeah, that'll work. So notice that these are all kind of charge based as well. Your full charges are going to be the strongest things here. So when you have full charges, that's when you're going to have your strongest forces. With dipoles and hydrogen bonds, you have permanent partial charges, which are not full charges, but just partial ones, so less than 1 as a charge. And then the London forces are just induced charges that don't last very long. So it's all about the charge here. Okay, let's see. What else can we do with this IMF stuff? Okay, so let's see. Remember, the more I can spell strength. Let's see. Yes. Remember, these have a lot of properties. High surface tension. Were those the three? Did we talk about capillary action here? Why not? So, I guess I can be consistent here. These would have high viscosity. So remember, there are consequences for having intermolecular forces. The stronger ones that you have, you end up with a higher boiling point or melting point. Both generally. You tend to have higher viscosity. Remember, viscosity is about flowing. So something like honey is very viscous; it flows very slowly. You'll have high surface tension, like water typically does. Surface tension is the kind of tendency to form a sphere, or like the inability to be to have your surface broken through. And then capillary action was kind of pulling up water against gravity or whatever other liquid you're dealing with, just due to intermolecular forces. I feel like we should probably touch on this as well. Okay. Remember, if you're looking at a molecule, remember, if it's going to be non-polar, you're looking for something completely symmetrical. If it's polar, it is asymmetrical. When you're looking at the Lewis structure. So this is kind of your easy way to check if something is polar. Another way to describe that would be any two electron domains are different. And this would then mean that all electron domains are the same. Okay, so that is our IMF in a nutshell. 8 minutes of intermolecular forces. Let's see, what can we do? No, I think that's pretty much all there is about intermolecular forces. So, hooray, we have that now. I don't know if there's anything more specific you wanted to go over with these, but that's kind of our crash course in IMFs. And then Crystal wants to do some density stuff, so we can do that. Alright, do some density stuff here. So remember, density is your conversion factor between mass and volume. So it is how you will go between the amount of substance something has versus how much space it takes up. So we'll start off with something super easy, just simple unit conversion. So we have a volume that we're given, we're asked for the mass, and we're given the density. So we would just set this up like any other unit conversion. Oops, because some of us can't put things the right way. We would just need to do this multiplication and that's it. 79. And from that we get 3.65 grams. Hooray! Remember that in any unit conversion you want to arrange it so that your units cancel out and you are left with the unit that you want. So this is just a one extra conversion factor. We can review some of our geometry stuff. There we go. Okay, let's try a slightly more complicated one. So, remember, a milliliter is the same thing as a centimeter cubed. So, we will either want to find our volume in centimeters cubed. Actually, it's what we're going to want to do. So we can either cube our 0.025 meters already, or we can convert that to centimeters right away, and then cube it there. Either way, you'll get the same answer. For fun, let's go ahead and do both. So the volume is, wow, that's shameful. There we go. Wow, there we go. If we do this, we can figure out our conversion factor between meters cubed and centimeters cubed. I mean, technically we have 1 centimeters cubed, 1 ml, and then we can have our density. So remember, for if you have cubic units that you're dealing with, you're going to have to cube the entire conversion factor. So remember, for our metric system here, we're going to have to cube our conversion factors. All these fun cubes everywhere, or we could just say 2.5 centimeters cubed times all this stuff. I think the second one is easier, but let's do both just for fun. 0.025 cubed divided by 10 to the negative 6th times 19.1. Lo and behold, we get this big old mass, 298 grams. Actually, we'll need 2 sig figs. All right, and if we were to do it the other way, 2.5 times 2.5 times 2.5 times 19.1. Lo and behold, we get exactly the same number because that's how unit conversions work. Again, I think it's easier to change your unit earlier so you don't have to worry about this cubic conversion factor stuff. But you do you. Whatever you like to do. Just double check. We have meters cubed, centimeters cubed, milliliters. We're left up with grams. Centimeters cubed, mils, left with grams. And in this case, we had to use scientific notation for our answer because it had 2 sig figs, but we needed to explain the number 300 with 2 sig figs. So that's where we would get that scientific notation from. So again, density is just a conversion factor for you to throw into your unit conversions. I guess we haven't done one with solving for a volume. Just so we can see it, I suppose. Here's a random one. What's the volume of 25.6 grams of a substance with a density of 1.29 grams per mil? So, start always with your measured quantity. We're going to want to put our grams on the bottom, 1 ml on top. .6 divided by 1.29, and lo and behold, we get 19.8. Hooray! We did it. So, dimensional analysis, aka unit conversions, is the answer to all your problems. So, whatever if it's stoichiometry or if it's density or whatever, it's all about unit conversion. So that's the big thing there. I wonder why my glasses always reflect blue when like nothing I'm looking at is blue. I have a screen that's got like black and white and the other one is just white, but what I see is blue. Go figure. So who knows? Actually, I guess these glasses are blue filtering, so maybe that's why they're like shining it back at everyone else instead of me. Who knows? But anyways, that's a tangent. Okay, let's go ahead and have a look. Okay, so we've done some density problems. We've done electron configurations and intermolecular forces and limiting reactants. What else would we like to do? We've got a few minutes left. Might as well put them to good use. Let's see. Yeah, there probably is a unit conversion for that. So it would probably involve wavelengths of light to deal with. So, yeah. I guess while you guys are perhaps coming up with stuff, so your exam is going to be 50 questions. It will be, I believe, 2.5 hours, which is 150 minutes. If you use a unit conversion, you can get that. So that puts you at approximately 3 minutes per question. So some of them will be simple, conceptual ones like, what's the formula for lead 2 nitrate? That should hopefully not take you too long to do. Some of them will be stuff like this where it's a simple calculation. There are a few that will require a few more steps. Nothing as long, this one again was too long to do as one problem. This would be like 4 problems in one. So if you could, like, for example, take these two and what's the product, that would be, a type of problem. Or, what's the Lewis structure of the sulfate ion. So it should be, it's doable in the 2.5 hours. Trust me. So, but you'll have all the questions visible to you, just like before, so you can maybe, leave the longer ones to the end, since they're all unfortunately going to be weighted the same. So focus on the easy, fast ones first, and then tackle the tough ones. Let's see, what other suggestions do I have? Make sure you sleep well beforehand. I know that's tough to do in finals week, but it's always better to be well rested before an exam. So, and then regardless of what happens, treat yourself afterwards also, because it is not easy to just sit down and take 2.5 hours of chemistry exam questions. So, whatever your way of rewarding yourself is, I would do that. Let's see. I will, thankfully, since I've seen pretty much all of your lab projects already, the grading of that should be nice and fast, at least for the group, part of it. With the individual stuff, that would probably take a little bit more time, just because I have to read through all of them and say, okay, who is Brittany talking about here, or who's Sherry talking about here, who's done absolutely nothing on the project, or blah blah blah, and that's where that's gonna take a little bit of time. I will probably submit your grades on Friday. Oh, I forgot, I have extra credit for you guys. I guess you'll want that, huh? It'll be just a survey on Google Forms that I'll post on Canvas. And it's just going to be, you talking about your experience with chemistry as an online class. So it's something just for me. I'm not going to be using it to give to anyone else or whatever. It's just for my knowledge, what do you think about the online class? Did you find, Discord was a good way of, communicating? Did you like the way I'm presenting material here? Stuff like that. So that one you can do after the final, of course. Don't waste your time right now. And that'll probably be like, 1 or 2% for your grade there. So just for a survey, that should take, like 15 minutes. So should be easy. But yeah, do that before Friday, I guess. So yeah. All right. So I've been stalling for time for like 5 minutes. Um, do we have anything else we'd like to go over content-wise? Here's Oz. Go ahead, say bye-bye to them. You won't see them for a while. Look at the camera. There it is, yes. Are you gonna show them your little sweater? Yeah. Oh, I know. Yay. It's been cold in Ridgecrest, so they get their sweaters on pretty much all the time, so. Let's see. I don't have Momo with me here this time, so only the Chihuahuas. Molecular geometry. Okay, finally something we can go over. Alrighty. Crash course in molecular geometry. Okay, let's do it. Okay. Okay. That's molecular geometry. Okay, cool. If we have two domains, we have two options. These are all going to be linear. I don't know why I even bothered. Hooray. Okay, no one cares about two domains anyway. Okay, let's reconstruct our chart. So again, it's going to be easy if you can throw them under their classification. How many atoms, how many lone pairs. For the electron geometry, it's all the same. For the molecular geometry, that's when things change. Remember, these are roughly 120-degree angles there. If you throw on lone pairs, they get a little bit smaller than that, but let's not worry about how small. With 4 domains, we have a few options as well. The shape here is tetrahedral for all of them electronically. Angle, of course, 109.5. Still tetrahedral if you have no lone pairs. If we have one lone pair, we go down to trigonal pyramidal. We have bent and then linear again. So it's kind of a good idea to make sure you can assign a molecule one of these kind of shorthand ways of talking about them. I can give you an example of each one. Oops. That would be one example of each of those types of molecules. For here, and then this one is going to be, I would have 2 lone pairs, but only 1 bond. That's strange. Oh, I know. That would work. And let's see. There we go. That would be some example compounds for all of these things. So yeah, so as long as you could identify, remember, let me replace those. M is the number of atoms. And N is the number of lone pairs on the central atom. So that's how we would kind of assign the shorthand to this molecule. We would look at it and say, okay, we've got one lone pair on it. We have 3 outer atoms, so we would call that AX3E. And then we would see that, okay, going back to our chart, AX3E is trigonopyramidal molecularly and tetrahedral electronically. So, and with 109.5 bond angles, etc. So, crash course in molecular geometry, done! Hooray! Let's see, what else can we do? Not much more with geometry stuff. Well, we'll see. Alright, we have time for maybe one more, like, topic. Maybe. Otherwise, I'll get the creature. I guess one more thing to note, the exam you do kind of have to do all at once. So you can't like do, half an hour here and then come back the next day and do the other 2 hours or something. You have to do it all in one sitting. So, yeah. Let's see. I guess I would also recommend going to the restroom beforehand. I guess Proctorio is going to probably, scream out alarms at me if someone's gone for like more than a few minutes. So, I don't know. Probably just easier to go beforehand, or like if you do go, like make sure it's not 10 minutes or something that you're gone. So hopefully there's no intestinal troubles, let's say, during it. Okay, let's see. Come here, creature. I know you figured in the most here with everyone. Is that so? Yes. Look at the camera, dude. Go say bye-bye. You'll see them in 111, maybe. Actually, I guess we'll hopefully be back on land when that happens. But we'll see. You're getting a little heavy, mister. Too many treats. Alrighty, well, if there is nothing else, good luck on your exam, everybody. You've got this. You can do it. And then you can have fun. Actually, I have no idea where your other classes have their finals, but you'll at least be done with this one. So, you'll be done with chemistry, and then you can kind of spend the next semester forgetting it all. if you have to take 111. So hopefully you don't forget it all, because the first couple weeks of that are kind of a review of this course. So the more you remember, the better it'll be. So good luck on that. Kind of sucks. I am hoping in the future that they will offer 111 in the spring, because it's kind of unfortunate for those of you who have to take it and you have to wait basically a year to do it. So sucks. So we're working on that. But yeah, I guess yeah, keep practicing your unit conversions. That's all I can say. Unit conversions is the answer to all problems, except molecular geometry ones, I guess, because there are no units there. Or we can convert degrees into radians. There we go. We can throw in our unit conversions here too. All right. Well, it's been a blast, guys. As always, if you come up with problems on the exam, shoot me a thing in Discord. That's the fastest way to get to me. If you're having trouble logging in or whatever, or if an image is not displaying properly, like if it's a graph or a molecular structure or something, let me know as soon as you can. I'm probably not going to be up at 3 in the morning though, so if you are taking the exam at 3 in the morning, I probably won't get back to you in time. So, yeah. All right. Well, other than that, take care, everyone. Enjoy your holidays. Good luck on your other finals. Good luck on this final. And maybe I'll see you in a few months. So we'll see. Alrighty.